Okay. So, um, single atom gases and diatomic gases have different number of ways in which they can wiggle. And those number of ways is what we call degrees of freedom. So, in general, the equipartition theorem tells us that the average energy is going to be, whatever the degrees of freedom is. Right, where this NKT is exactly the right-hand side of the ideal gas law. So if we've got argon's a noble gas. It stays as a monoatomic element. So the degrees of freedom are just 3. It can move in the x, y, or z direction. So if it has only kinetic energy, then we have 1/2 mv squared equals, degrees of freedom is 3, so 3/2. And then n here is number of particles. If we're just considering a single argon atom, then that's just going to be 1. Boltzmann's constant is a number we have to look up, and the temperature has to be in Kelvin. So 2500 Kelvin. Yeah, chemists will say PV equals nRT, lowercase n, capital R, where this is the gas constant, and this is number of moles. And then the capital N for physicists is number of molecules, and Boltzmann's constant. All that means is that capital N is Avogadro's number times bigger than little n over here, and then Boltzmann's constant is Avogadro's number times smaller than big R. So the right-hand side is exactly equivalent. It's just physicists are usually talking about small number of particles. So we like Boltzmann's constant, and chemists are usually talking about large numbers of particles. So they like the gas constant.
Oh, so you said that big N is smaller than little n?
Yeah, well, big N is Avogadro's number times little n.
Oh, because I thought it was n divided by Avogadro's number. Because the way I was doing the math, I don't know.
So,
but I guess we could go over the math.
Yeah, so big N is number of particles, right? And Avogadro's number is particles per mole.
Yeah. Oh, yeah, I guess. Yeah, I guess so. Now that I'm thinking about it.
Alright, so we come back to our energy equation over here. We get the halves to cancel off. And V will be the square root of K over M. K is 1.38 times 10 to the minus 23. Right, that's literally just 1 over Avogadro's number. And what's the mass of an argon atom?
39.95 grams.
9.95 what?
Grams.
A single argon atom is 9 grams?
No, I'm sorry. So 39.95 grams.
For one argon atom.
Yeah.
Seems like a little much.
Well, I don't know. I just got that from the periodic table.
So the number there is 39.9 grams per mole of argon.
Okay, per mole. Sorry.
But we don't have a mole of argon. We just have one argon atom. Right? And 40 AMUs is 6.6 times 10 to the minus 26 kilograms. Right? So we're in SI units here. Kelvins, kilograms.
I'm sorry. How did you get that? How did you get that?
I went to Google and I typed in 40 AMU to kilograms.
Oh, is that what you do?
That is what I do, yes.
Okay, so that's much easier. It seems like I know I've seen the other dude that I watch who helps me, or he does the work, and I saw him do AMU, but then the other one just did something else. So I should always convert from AMU to kilograms when doing this.
For this class, yeah.
Finding
We
always?
we should be a
I'm trying
number
to
of
find-
particles, kilograms, Kelvin, right, and joules.
Oh, so when doing VRMS, when I want to find the mass, I should always convert from AU to kilograms.
Yes.
Okay, awesome.
Yes. The AMU is also called a Dalton.
Oh yeah.
After the same guy whose Dalton's law was named after. It's definitely a chemistry thing. Yeah, you can also just search mass of argon in kilograms in Google. Absolutely. All right. So then, now there's just calculator work left. Anyone got a number for me? Yeah. So it's about 1,200 meters per second. That is fast. Alright. Yeah, it's just a particle of gas. It's zipping around. Even though the bulk gas isn't going anywhere, the individual particles are definitely moving. Does that answer your question here, Jazz?
Yeah, thank you.
You're welcome.
Alrighty, Yusuf, what's your question?
Yep, we can do some toolbox work here. So what we just went over is the equipartition theorem. And there's several equivalent ways to write this down. I usually think of it in terms of the energy per degree of freedom for a molecule is equal to 1/2 kBt. Right, so for a monoatomic gas, the total energy is 3/2 kBt per molecule, and for a diatomic, it's 5/2. We also have another kind of elastic deformation, but this time due to temperature. So we know that if we apply pressure to a thing, we can crush it. But if we apply heat to a thing, we expand it. Where this alpha is a material-specific constant. We have the ideal gas law, which you should already have from chemistry. Except instead of little n RT, we write big N kBt. And the units of these things, they're always going to be pascals, cubic meters, number of particles, right? Boltzmann's constant. And temperature in Kelvin. So we don't play the same games chemistry does, where sometimes the volume is in cubic centimeters, sometimes it's in liters, sometimes the pressure is in millimeters of mercury, and sometimes it's in atmospheres. No, it's always pascals. 13.5 introduces us to the concept of PV diagrams. And this is how physicists map out phase changes, like where, in what region of pressure, temperature, space are materials expected to be solid, liquid, gaseous. And actually, we get a little more specific than chemists there, because we, like, for example, my PhD research involved phase transitions from one solid phase to a different solid phase. it's also much cooler, right? The way things are arranged on an atomic level, like, matters. You ever wonder why the salt that you get from your salt shaker is tiny cubes? It's because the atoms are arranged in cubes. Right? Because the atoms themselves are arranged in a cubic formation, there's a high tendency for them to break along those atomic planes, and you get cubes at the macro level because it's cubes at the micro level. But there's no real tools from 13.5. 13.6 kind of goes over, what relative humidity means, and we'll probably be doing, we probably won't be doing any calculations from that section because it's literally just a lookup table at this point. So that's it. This is all of chapter 13.
Oh wait, Dr. Wolf, I have a question. So what about change in area and change in volume? Like, you know how for those we can't, I know the change in area equals 2A times big A times change in temperature, and the other one is change in V equals the constant for volume times V times change in temperature. So if we use those on the exams, would those be considered like magic equations or something?
No, it's the same relationship, just like we had for the elastic relationships.
So if you just write that without deriving it, we'll be fine. I don't think we can derive it though. It's a little bit hard too.
Yeah. So for example, the coefficient for volume is just 3 times the linear coefficient. That's it.
3 times linear coefficient?
Yeah.
Okay. So is it okay if we just put B, V, change in T?
Yeah, and then you look up the beta from like Engineering Toolbox.
Okay, and then we don't have to. I'm sorry. We don't have to. So if we write that, it's not going to be considered as a magic equation.
No, I mean this isn't actually. This is what we call an empirical relationship. We observe this relationship to happen.
Okay.
And we do statistical fitting to get what the alphas are.
Okay, and also PV equals nRT. Would that be a magic equation?
Just don't use it.
Oh man.
Right?
Okay.
Practice using it the physicist's way when you're in a physics class.
Okay. Also, do you know the formula PV equals 1/3 N MV average squared? Can we use that equation?
So that is putting the equipartition theorem and the ideal gas law together.
So, let me see how that would work.
Right? Because this KBT here, for gases, that's going to be PV over N.
Yeah. But I don't know, where would the 1/3 come from though? That's a little bit bizarre to me.
What do you mean?
Like, so PV equals 1/3 NMV average squared. I don't know, like, how is that formula derived though? Because it looks like, I don't know where the 1/3 came from.
The 1/3 came from there being 3 degrees of freedom. So you can move in the X, the Y, and the Z direction. On average, you will have the same amount of velocity in the X and the Y and the Z direction. So 1/3 of your squared velocity will be in the X direction, 1/3 of it will be in the Y direction, 1/3 of it will be in the Z direction.
Could we please derive that? Or, I'm sorry.
Yeah, no, it's totally fine. It's actually done in detail in the gray box in 13.4.
Yeah, I saw, but it didn't show how to get from that to PV1. It just showed how to get that to something else, I think.
Okay.
Let me see again. I'm
So
not sure.
our velocity, our total velocity, we remember from our kinematics days, we could write this as Vx comma Vy comma Vz, right? Does that look familiar?
I'm sorry. Yeah.
So if we want the square of the velocity,
Oh, I see it. Yeah.
yeah, we just use the Pythagorean theorem.
Okay, so we just do that. Awesome.
Right. And on average, all three of these should be the same size. So we should get, Vx squared average is equal to the average of Vy squared is equal to the average of Vz squared is equal to 1/3 the average of the total velocity squared. Does that make sense?
Yeah.
So the 1/3 comes about just when we are trying to figure out what the velocity in a specific direction is.
Okay, got it. So there's another formula. I'm sorry. There's this one called. Or do you want to finish this, or do you want to stop right there?
Finish. Is that not?
Oh yeah, it is. I think. Yeah.
Okay.
Sorry. So for the second formula, there's this one called change of v equals 1 over b times f of a, or f over a times initial velocity or initial volume. So how
Wait,
how
say that-
how is that one derived?
Say
That
that
one's
again?
really. I'm sorry. So it's a change in volume equals 1 over b times f. Oh, sorry, b, not v. B as in baby.
Is it B or beta?
Or beta, or I don't know. I think it's like it's the same one as the other one.
Yeah.
The other, yeah. So times F over A, or you could say pressure, but I guess F over A would be better because it's, yeah. And then initial volume times initial volume. So how is that one derived?
This is exactly our bulk modulus definition from chapter 6, right? Just rearranged a little bit, right? So if we divide, so we're used to seeing it like this: delta V over V times beta equals pressure.
Yeah, I don't know how the beta got down there.
You just got
So-
divided off.
Oh, I see.
So pressure
I
is
see,
F
never
over
mind.
A. We multiply it off the V. We divide it off the beta.
Wait, you said this is from chapter 6?
Yes.
We did this in chapter 6?
We didn't test on it, but we did have a lecture on it.
Oh, okay, so got it.
So we are bringing this back because if the idea is if we apply heat to something that is not free to expand, instead of expansion, we get pressure. Does that make
Yeah.
sense?
Yeah.
Yeah, so if you heat a rod, it wants to get longer, but if it's stuck between two, say, concrete pylons, it can't get longer. So instead, the concrete pylons have to exert pressure inward in order to compress it by the amount it would have liked to expand by.
Yeah. Okay. Also about partial pressure formula, would that be considered a magic equation for the partial pressure?
No, that's Dalton's law of partial pressures.
Okay. And then so you said humidity formula is also it's not going to be, but you said that we might not use it on the exam.
Well, you almost certainly will not use it. There's too much else in this chapter that I've got to focus on.
Okay. And then how about so? Oh yeah. So okay, we'll just skip
So
that.
I just realized Yusuf had a question about the cubes. That he was still stuck on the
Oh,
cubes like 10 minutes ago, and I ignored him, and I'm so sorry. Um, give me 1 second.
sure.
So so if you have salt, salt is NaCl, right? Imagine a cube, right? I'm going to do my best to draw a three-dimensional thing. That's actually not a bad 3D drawing. Okay. So when I say it's cubic on the micro level, what I mean is imagine you have this cube. On each corner of the cube, there is an atom. There's sodium here, 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 and here. And on the other corners, there's a chlorine. And that is actually how salt organizes its atoms on the atomic level. Right, so all of these edges on the cube are ionic bonds between chlorine and sodium, and then all of the vertex are atom locations. Yeah, all table salt is like that on the atomic level. Right, so if you have a chunk of salt and you go to mechanically break it, it prefers to break along these faces. These are called cleavage planes. So they're planes that minerals prefer to break along. Essentially, that's how you cut gemstones too, right? Like you can't cut a diamond into any shape you want. You can only break it along the cleavage planes of the diamond to get certain shapes. And salt is the same way, except it only has one cleavage plane, just the faces. Right, it's not malleable, so instead of deforming, it'll just crack. And the cracks will almost all of the time split one of these cubes from its neighboring cube. And that's why you tend to get little cubes of salt in your table salt. You are welcome. All right. You had another formula that you wanted to ask about, Jazz?
I don't think so. I was gonna ask. So for 13, you think are we gonna skip 13.6? Like,
I mean, in the sense that I'm not going to test on it. Yeah.
okay, yeah, because I had a question about something, but okay.
I mean, feel free to ask the question.
Oh, I'll save it last just in case if we run out of. I don't want to make sure that we don't run out of time, or I want to have all my questions answered. So I'm gonna leave that as my last. Okay, so I think so. Did I ask you? I think I said is partial. Oh yeah, you said it's okay because you said Stolten's definition. Okay. Um, have all of them. So yeah, I think all of the formulas are looking good. I have a question about 30. I think it's about 33. I think no. Which one was it? Let me see. I'm sorry. Or was it? Maybe not 33. I mean, it is 33, but which one? It was something about. It had temperature and it had volume. Or no, temperature and yeah. Or maybe not. Let me see which question was that. I'm sorry.
It's okay.
Oh, I found it.
Okay.
Okay, 15. So I was gonna ask about 15.
15.
I was, yeah, I was confused because the formula P1 V1 T2 equals P2 V2 times T1.
Sounds like Charles's law.
Yeah, we don't use that, right?
We don't do that here.
Okay, I think. Oh, I was wondering why we wouldn't use that formula, but I guess you said why.
Because it's just a special case of the ideal gas law.
So, okay, never mind. I guess I don't need that equation. So we don't ever use Charles' law ever.
Nope. We always go straight for ideal gas law, and if things cancel, they cancel.
I'm sorry. So actually, we should go over this one because, like, okay. So why wouldn't we use PV equals nRT like for that one, and then like have two equations like that, and then say nR is constant, or like what? Let's see what else would I say is constant. Like okay, like the pressure is constant, and so is the NK. So would we say? I don't know.
Mm-hmm.
Yeah, something like that.
So Boltzmann's constant cancels. We're not allowing the quantity of gasoline to change, so the ends cancel. The pressure is not changing. It's being allowed to expand in volume instead. And so we get V1 over V2 equals T1 over T2. But this, what systems does this apply to?
Ideal gas.
Mm-hmm. And what is it that we're dealing with in this question?
I don't know. Gasoline?
Gasoline. Is gasoline a gas?
No.
It is not.
Oh, okay. That makes sense.
So instead what we want, right, is not this, because we're not dealing with a gas. What we want instead is right? So we know everything here except for delta V and beta. So delta V we can solve for. And beta we have to look up. So what is the thermal expansion coefficient for gasoline?
For gasoline. 950 times 10 to the negative 6.
Correct.
Yay.
And what are the units on that?
Good question. Let's see. So let me go to, let me go to 13.2 again. So 1 over Celsius.
Yes. So the change in temperature that we're looking at is 16 degrees Celsius. So these two units are actually going to cancel.
Yep.
So we just have a volume unit on the left-hand side, and we have a volume unit on the right-hand side. So we don't actually have to convert to meters cubed if we don't want to. We can just, like, whatever unit we have on the right-hand side will also be the unit we have on the left-hand side. The 16 degrees is 35 degrees minus 15 degrees.
Oh, would we change of V to, just to make it easier, to final V minus initial V? Because it's asking to show that.
Yeah.
Yeah. I think this would be easier. I mean, we could have added it to the initial value, but...
Yeah, so our final volume is going to be all of this thing plus 60. And then all of this stuff is how big?
Well, they didn't, so that's not in scientific, the first one is not in scientific notation for proper scientific notation.
That's fine. Your calculator will deal with it just the same.
Okay, so he said Yusuf got 1.14 for the total? Yeah, I think the total.
Also, 35 minus 15 is totally not 16, it's 10. So, I don't know why I said 16 the first time.
Oh, because you thought it was 31. Oh, it's okay. Let's see. Where's my calculator? I just...
Yeah, I get 0.57 as well.
So yeah, so that's the three terms are 1.14, and then you add 60 and you get 61.14, which is close enough. I mean, if you round it, you get 61.1.
I'm sorry, say that again?
Oh, sorry. So Yusuf said that the three terms, when you multiply them, you get 1.14, and I got that too. Like, exactly 1.14. Sorry. And then after that, what do you mean, Yusuf? It is 20. 35 minus 15 is 20. Yeah, I am right. Okay. So when you multiply those three terms together, you get 1.14. And then you add 60 to 1.14 and you get 61.14, and then that's
35 minus 15 is 20.
Yeah.
Wow. I need more coffee. Yes, it's 1.14.
Yeah, and then you add it at 61.14 and you round it, it's 61.1, so yeah. Oh, I was gonna ask you something. Um, so when do we? So besides, like I know, so you just said that we have to use.
It's
It has.
11 o'clock.
Ooh, I'm so sorry. My computer does that. Um, yesterday I forgot to turn it off in class and everyone heard. But okay. So yeah. I was gonna say this. So for in order to use an ideal gas law, besides like besides it I know it must be it must be a gas in order for us to use the ideal gas law.
For sure.
What is the other condition? Like what are the other conditions for like? Can we always use it when we're dealing with a gas or not?
You can always approximately use it. So the assumptions that go into the ideal gas law are that it's a monoatomic gas that is small, like the actual particles are small, and the molecules don't really interact with each other very much. Right? So, like, they don't collide with each other, they collide with the container walls. Right? And those things are, like, approximately true for gases that aren't, like, super dense. Right? Not exactly true, but approximately true.
Yeah. So you said monatomic, right? I think the book said that by monatomic they mean like all, like they said that it's all of them or something. I don't know. I don't like. I can look up where it said something about that. Like,
What do
I
you
don't know
mean?
how to spell it. So they said that here, I should. Oh no, there's no search result. They were talking about that. Something they said that. Okay, so if it's diatomic, can we still use it though? Like if it's H2 or N2?
Yeah, it won't be wrong by much. You know, there are chemical engineers who spend their lives like measuring the fraction by which the ideal gas law is wrong for various gases. But as long as you have small molecules, you're not off by very much.
As long as we have small molecules, you said?
Yeah. You get into trouble when you have large complex molecules, like sulfur hexafluoride is not like you start being off by like 10% when you get molecules that large, and molecules that have a magnetic moment, or which are ions and have some electrical charge. Those ones, the ideal gas law doesn't work so well.
Okay, so on the exam, can we always, like, do we have to worry about that though on the exam? Like, can we just use it if we just see if we are dealing with a gas? Like, if I see a gas, can I automatically, like, think that
Assume
I
it's
can
ideal.
use? Yeah.
Yeah, in this class for sure.
Okay. Yay. Okay. That made me happy. Okay. That's my. Okay, so yeah, I'm good with that one. So what? I wonder if Yusuf has a question. Oh yeah, he does. 34. He said.
Okay. Oh, you had to pick the novel. You always pick the longest questions, Yusuf.
He knows what he's doing.
Yeah, he does. Alright, so we have a high pressure gas cylinder containing something toxic at a high pressure. This is like 100 atmospheres of pressure. And ambient temperature. So if the cylinder is cooled, say via dry ice to reduce the leakage rate and pressure, what is the pressure in the tank after it's been cooled? Okay. Alright, so we note right away, like, hey, isn't this just a Pascal? And yes, it is a Pascal. So P1 V1 equals N1 KB T1. Just the ideal gas law. Just ideal gas things. So here, we're containing it in the same cylinder, so the volume isn't going to change. The amount, we're not allowing it to leak out, hopefully. So the amount of gas is going to stay the same. Boltzmann's constant is a universal. And so we get P1 over P2. And if someone calls this Boyle's law or whatever, like I'm gonna lose it. So what is the pressure after it's been cooled down? So we're solving for pressure 2. The original pressure is 1.4 times 10 to the 7. The new temperature is minus 78.5 Celsius. And this is the temperature has to be in Kelvin for this to work out. So 273 is 0 Celsius. Right? So 273 minus 78 is going to get us something like 195. And it was originally at 25 Celsius, which is a temperature of 298. Nobody's got time for the 0.15 on the end. Yeah, so far so good here. So we reduce the pressure, by about 40%. Still not great. We went from 140 atmospheres of pressure to 90 atmospheres of pressure. It's still very high pressure. What if 10% of the gas escapes and kills half of the people that are handling the cylinder? That's part B. What? They said it's toxic. They didn't have to say it was toxic before they talked about a leak. Textbook brought this on themselves. We can assume they left safely? How can we assume that? They're here cooling it down so they can repair it, right? Alright, I guess gas masks are a thing. That is true. You've got me on that one. So if we have some of the gas escaping, now our ends don't cancel. So we'll have P1 over P2 equals N1 T1 over N2 T2. And then if 10% of the gas escapes, then that means the amount of gas that's left is 90% of what was there at the beginning. Now the N1 cancels, and we get P2 equals 0.9 P1 T2 over T1. So now we've only got, what, 80 atmospheres of pressure. All right. And then last question. How cold would you have? So, any questions about this pink part here? Are we good on the pink part? Okay. Oh, yeah, that's right. So, the thing we got for part A is all of this bit here. So plugged in that, multiplied by 0.9. Bob's your uncle. And then let's assume, so for part C, there's no leakage and we're just changing the temperature. And we want our second pressure to be 1 atmosphere. So we can solve this for T2 instead. So T2 equals P2 T1 over P1. The second pressure that we're looking for is 10 to the 5th pascals. That's 1 atmosphere of pressure. So we get a pretty small number here. Would it be feasible to chill this gas to 2 Kelvin?
I don't think so.
Yeah, it would be problematic. That's colder than liquid helium. So we would need to... liquid helium is as cold as we can go unless we have a laboratory setup. By the way, do you know what the coldest something has ever gotten in a laboratory setting is? You want to guess?
Yeah, zero kelvins.
You can never get to 0. That's impossible.
0 point something something. Yeah, 0.1.
It's a lot smaller than 0.1.
0 point something something. Can we say that? Yeah, 0.000001.
Yeah.
Oh, sorry, I didn't add enough zeros.
So it is possible to cool things in a laboratory setting down to a billionth of a Kelvin. So that is approximately the right number of zeros there. Zero Kelvin is impossible. Again, that's one of the laws of thermodynamics, actually. To completely get down to 0 Kelvin, you'd have to completely remove all entropy from your sample, and that just isn't possible. Not even in principle is it possible. FYI, this 2.1 Kelvin that we just solved for, that is colder than outer space. So deep space has a temperature of approximately 2.7 Kelvin, just due to all of the background radiation. Okay. No, radiation is background radiation is why the temperature isn't 0. Right, so even in the absence of all matter, there is still a temperature due to the energy of the background radiation. All right. So do we have another question that we want to... I do not like that one. I do not like it, Sam I am. Okay, a bicycle tire has some pressure. Looks to be about 7 atmospheres of pressure at a given temperature and contains 2 liters of gas. What will its pressure be if you let out 100 cubic centimeters of gas? Or what would be 100 cubic centimeters at atmospheric pressure? Okay. We're gonna use the ideal gas law. No. I'm going to take the one with Porter. What?
Oh, sorry, we were talking about something. We were talking about next semester.
Oh, okay.
You're not teaching next semester, right?
I am, but I'm teaching engineering students.
Oh, okay, that's why we couldn't. Yeah, we couldn't find you.
Yeah, sorry. But you can have the link to my 152 lectures that I did this semester.
Oh, you're not going to delete that if you go in person, or if your class goes in person?
Hell no, I'm gonna leave it up there forever.
Thank you.
That's that YouTube channel is my resume for the next job I apply for. Pravika and Pang are both perfectly fine teachers. Pang is stricter. So if you are prepping for the MCAT, that might be a good idea.
I'm sorry. Did you say it was stricter?
Dr. Pang is stricter, for sure. He also He's the only person in the building that does more office hours than I do.
Oh.
So he really does work hard to try and teach.
Oh, got it.
His exams were multiple choice? Yes, he does have multiple choice as part of his exams. And frankly, next semester I probably will too. Just because grading 800 free response questions for every exam is just so much. So anyway, let's analyze first this amount of gas that's going to be let out. All right, so PV equals NKT. If the amount, how much air are we talking about? Hi, Miss Abigail. On Friday, we're going to do chapters 13 and 14. If we're looking at 100 cubic centimeters of air being let out, 100 cubic centimeters is how many cubic meters? Oh, no, we're done with fluids. I mean, technically gases are also fluids, so... yeah, Yusuf's got it. So there are 1,000,000 cubic centimeters in a cubic meter. So 100 cubic centimeters is a 10,000th of a cubic meter. So I get this is 2.5 times 10 to the 21. And this is the number of air molecules that escape when we let out that much air. So how many air molecules are there? Maybe we'll call this delta N. No, not delta N. We'll call this N. That's the amount of molecules that escape. How many molecules of air were there in the tire before you let out some air? Yeah, I mean, you're solving for the number of molecules is something that a chemist would find horrifying. So there's a little bit of a hurdle there to be jumped.
Dr. Wolves, why did you write 10 to the negative third?
Because that should be 2 times 10 to the negative third. Because a liter is it's 1,000 liters in a cubic meter.
Oh, okay, sorry. Thank you.
Yeah. And then so I get 3.5 times 10 to the 23. So about half a mole of gas. So that N3, which is how much gas you have after you let out some gas. Right, it'll be like, so 3.5 times 10 to the 23 minus 2.5 times 10 to the 21. It's a real small difference, right? So maybe we can rewrite this. We can say this is 350 times 10 to the 21, and that'll make the subtraction easier. Alright, so it turns out I may have rounded too aggressively. But you get the idea, right? Now that we know the new amount of gas, we can say, well, then our new pressure is going to be equal to my aggressive rounding bit me in the rear on this one. So all right, questions or comments? Did you want to do a different one, Jess? We've got time for one more.
Are we gonna find P3? Sorry.
Oh, I have to go back and input these calculations again because I rounded too hard.
Okay, so what would V be? I think. Let's see. It would be for the P3. Like, what would V3 be?
That would be the same volume, 2 times 10 to the minus third.
Because on the other one you have like that one's like 1 atmosphere and the other one's 2 times 10 to the negative third. So why would you use 2 times 10 to the negative third instead of the 1 atmosphere one?
So we're because P3 is still inside the tire, right? And the tire still takes 2 liters of gas. Right? Because a gas is going to fill its container completely.
Okay, so Okay.
Does that make sense?
I think so. So the N1, so what's N1? Is that like the amount of air that you take out?
Yeah, that we took out. The number of air molecules that we let out.
Okay. Got it.
There we go. Alright, so then we can use this as our N. Okay, so we ended up letting out less than 1% of the gas. So even though 2.49 times 10 to the 21 molecules sounds like a lot, it's not. It's not a large. It's not actually a large amount, or it's a large number of things that are individually small. We get 6.94 times 10 to the 5. Yeah, so the pressure only dropped a couple percent. Or actually 1%. So are we more or less done? Or have we been brain mushed?